It is a great pleasure to me to introduce Alejandro Cabrera. He is from Universidade Federal do Rio de Janeiro. And today he'll speak about Lie theory for groupoids and compatible geometries. Thank you, Alejandro.
Okay, so I will start thanking the organizers, Romina and the others, for the invitation. So I'm going to speak about something that it's probably is related, but it's not very directly related, probably with the other talks. So I will try to, spend more time in the concepts, and then only at the end mention some of the work that I have done with some collaborators. So the structure of the talk is like this. There will be an introduction. Then, as I said, I will spend some time trying to explain what the concepts are and how they, at least for this talk, how they came about. In particular, this idea of Lie groupoids and this generalization of Lie theory. And at the end, I will mention some results. Okay, so I'll try to be quick. So let me start with the introduction. So first of all, the main definitions behind the talk are these things called Lie groupoids and algebroids. For you to have something in mind before I try to introduce them, these include Lie groups and Lie algebras. And also they include the actions of Lie groups and Lie algebras as symmetries on manifolds and so on. So we can think of this as a generalization of standard Lie theory and all its applications. And there is another aspect that I will be speaking about, is that the cases in which these groupoids, whatever they are, they don't come alone, but they come with extra geometry on top of them. For example, if you think here, it would be the case that you don't just study a Lie group, but a Lie group with maybe a Riemannian metric or some other geometry on top of it. And there are two, at least summarizing, there are two currents of motivation for this. The one that, this right one, that it's more related to the talk that I'm going to give, is more related to the symplectic side of geometry, which is a bit separated as sometimes from the more classical side of geometry, like Riemannian and foliations and so on. It's related to mathematical physics. Ultimately, here I just summarize three key things. So one is the study of symmetries in symplectic geometry and Nether's theorem, conserved quantities, and so on. This gives rise to a lot of structures that are related to the things that I'm going to speak about. The other thing is that just as symplectic geometry, symplectic structures come from mechanics and the description of dynamical systems and so on, but then they were studied as geometric objects. The same happens with Poisson brackets. So there is an area called Poisson geometry, and it has other generalizations also motivated by mechanics. And then there is another third aspect, which has to do with quantization and the relation to quantum mechanics. So this is a very deep connection between non-commutative algebras and geometric structures. Just to have something in mind, here you can have a quantum group. Doesn't matter. It's a Hopf algebra, and the geometric side of it, it's a Lie group. Let's say we call it H. But it doesn't come alone. It comes with additional geometry, which is a Poisson bracket. I will explain what these things are in a second, but just to say what is the spirit of these things, that in most of these cases, there are two types of structures and they come together in a compatible way. There is another front, particularly with respect to groupoids, which comes from more classical maybe studies, like the study of foliations, the holonomy groupoid. Then there is a connection to singular spaces, for example, orbifolds and generalizations of orbifolds, and even more generalized, more singular spaces called differentiable stacks. And also there is a connection to non-commutative geometry where groupoids play an important role. But I will be focusing more in this side of the story, although the definitions are the same. So this is in red here. You can see that what we are going to do is to review this Lie theory for groupoids, and also how the compatible geometry on these groupoids also can be differentiated to infinitesimal level or integrated to the finite level, just as Lie groups and Lie algebras can. So let's begin quickly with this. So the first thing that I want to do is to give you an idea what these groupoids are. I'll start with groupoid, which is an algebraic structure independent of the Lie modifier, just as group is an algebraic structure. And there are many ways to present what a groupoid is. One that I'm going to use here is as an analog of an equivalence relation in a set, but now it's enriched. So let me draw this. So we have a set. On the left, we have equivalence relations, which we all know. And the idea is that in a groupoid, we enrich the equivalence by considering a set of the possible ways in which X is actually equivalent to Y. For example, if X was a triangle and Y was a triangle, there is the information saying that these triangles are equivalent, but there is more you could give more. You could say they are equivalent through this particular rotation or through this particular translation or so on. So this extra data is enriching the fact that the objects are equivalent. And then the structure of the groupoid can be motivated by following the axioms of an equivalence relation. For example, every element is equivalent to itself, and then you think that among all particular arrows like this, there is one that is distinguished called the unit. This reflexive property we promoted to the idea that whenever I have an arrow like this, the blue one, there is also an inverse arrow. And the transitivity we encode in the idea that when we have arrows that can be composed as arrows, you can actually compose them, and there is a third arrow that is the composition of these two. So with this motivation, what you get is an algebraic structure. So there are two sets, the sets of all objects, the set of arrows. There are two maps called the source and the target, which are where the arrow begins and where it ends, the unit, the inverse, and the multiplication, and there are natural axioms that these satisfy. If you want to think of something concrete, you can think that G is the set of morphisms in a category, and the axioms are just those of a category where every morphism is invertible. So something that is nice about this analogy is that there is this has more information on the right, and there is actually an induced equivalence relation on the set M, but there is more information. For example, what are called isotropies, which is that an object can be equivalent to itself in many different ways, and you have the set of all those possible. This is part of your information. Okay, So now let's think quickly about Lie groupoids. So this is very parallel to the idea of Lie group. So there is the algebraic part of the structure, and then there is the smoothness condition. So in this case, it means that the set of all arrows is a manifold, has a manifold structure, M as well, and all the structure maps are smooth. There is also one includes the condition that the source map is a submersion. But this has many consequences. One of those is that the induced equivalence classes in M is not just any partition. It's actually a smooth foliation, but it's singular in the sense that the dimension of the leaves can change, but it's still smooth in a very specific way that I won't mention, but one can make very precise. So the smoothness, for example, has this particular consequence. Another consequence is that the set of all self-equivalences, it's a Lie group, actually. So there is a very rich geometry behind these objects. Let me give you quick examples to see what we are dealing with. There is a very simple example called the pair groupoid, which is the case, oops, something went wrong here. Is a case essentially when there is no information. So you put no extra information. You just declare that every 2 points are equivalent, and the only information that you have is which are those 2 points. So this as a set is M cross M. Composition is a very trivial operation where you delete one of those. This is more interesting. Suppose that you have a Lie group H acting on a manifold. So the idea is you consider pairs X and let's say H. And well, the arrow, you think that the arrow starts at H, but it ends at the action of H on X. So as a set is a Cartesian product, but it has this groupoid structure. And of course, the equivalence relation induced on M are the usual orbits, and the isotropies are the usual isotropies, and so on. And here we can see how Lie groups are particular cases of groupoids. If the set M has only 1 point, then essentially you just have the group. And so it's an abstract way of seeing elements of any group as isotropies of an abstract element here. Another interesting example that comes from differential topology, let's say, is this. It's called the fundamental groupoid, in which this object is an homotopy class of paths. So you have a path gamma, let's say, going like this. So the equivalence relations would just tell you that these 2 points can be joined by a path. But now we have more information. We know, for example, the homotopy class of this path. So we know if it goes around in this side of this hole or on the other side. So this is another example where we see this this enrichment going on. This is called pi1. So the isotropies you see are the fundamental group associated to the point. And moreover, if you consider all the arrows that start at a particular point X, this gives you a model for the universal cover of M. So we see that these things, although might seem abstract at first, they actually have very useful way of packaging all sorts of information. This is another example that I put. So we have a vector bundle. If we have an element of this vector bundle in the fiber over X, we see that as an arrow, but going from where to where? Well, x to x. So we only have arrows from x to x. We only have isotropies, and the composition is just the addition of these elements in the bundle. So this is the total space of E. Okay, so we have all these examples. This one can be refined also for the study of foliations. If we have a foliation, we could consider only paths that lie entirely inside the leaf of the foliation. And instead of considering homotopy classes, we could consider holonomy classes with respect to the foliation, holonomy classes of paths. And the construction is very similar. And it's interesting that this fits into a manifold. Could be non-Hausdorff, but typically we allow this in the definition, the total space. And this is called the holonomy groupoid of the foliation. This is one of the, this is an example of a groupoid that enters naturally, let's say, classical geometry studies like the study of foliations. Okay, so I hope I gave some idea of this. Then let me go quickly into the Lie theory of this. Just as Lie groups have, if you think of them as transformations, they have infinitesimal transformations, analogs, which are the Lie algebras. Here, something similar happens. To get the infinitesimal information, we could think of families of arrows that go to the identity, and the first order information will be our candidate to the algebroid information. So if you think of this picture for a little while, you can guess actually the definition of what a Lie algebroid is, and also how, given a Lie groupoid, you can associate a Lie algebroid. Just as when you have a group, you can associate the Lie algebra. So this A sub x, for each x, you have first order linearized information. This becomes a bundle. Then there is this idea that the derivative can be seen as a tangent vector at the identity. But because the source was fixed, you can also precompose or compose on the right with some h, and you can get a tangent vector at any other element h, and this defines right invariant vector fields, just as in the ordinary case. So you have a bracket induced from right invariant vector fields. And there is also this piece of information called the anchor, which tells you infinitesimally where this y is going to first order. So this will be x plus the anchor of A of x at order epsilon plus higher order terms. So because this bracket was induced from vector fields, it satisfies. So this bracket, you can see it as a bracket on sections, and it satisfies this kind of Leibniz the property. So it's of infinitesimal nature with respect to this anchor map. Okay, so this is the quick version of what the infinitesimal version is. And there is an analog of Lie theory for these things. In particular, there is a Lie functor that takes a groupoid to the algebroid, as I mentioned above. And there are analogs of the classical Lie theorems. For example, if you have one algebroid that comes from a groupoid, then there is a unique universal cover, let's say. But now the covering happens along the source fibers, just as we saw in the case of the fundamental group. So this is very parallel. So all the groupoids that correspond to a particular algebroid are related by covering. There is something about morphisms that if this groupoid G1 is simply connected in the source fibers, then there is a unique integration of a morphism. Here I put more or less the year for you to see, have an idea of the development of this area. This is from 2000, although the motivations and these results were acknowledged before, but the details come from 2000. And then there is this third Lie theorem that would say that every algebroid comes from a groupoid, but this was known from the start of the, let's say from the early 80s, that there were counterexamples. You could show that there is an algebroid that doesn't come from a Lie groupoid. And so the particular theory of obstructions telling you when yes, when no was developed in 2001. And this paper was very important, was published in the annals for the area. So let me just very, very quickly, I hope this gave you an idea of this Lie theory for groupoids and algebroids, but there was something else in the title, which is the compatible geometries. And so I want to tell you about a particular case of all these constructions above that is related to Poisson geometry, in which the groupoids, they don't come alone. They come with a compatible symplectic structure. So let me go quickly over this. So what is a Poisson manifold? Very quickly, it's a Lie bracket on functions on a manifold that also satisfies this derivation property. Because of the derivation property, you can see quickly that this is actually a tensor. It's defined by a tensor that is called Poisson tensor. And symplectic manifold are particular cases in which this tensor is non-degenerate. If you invert it, here there is an inverse missing. So if you invert it, you get a two form that is the standard description of symplectic structure. It's a closed two form and so on. Okay, so what happens in Poisson manifolds? The idea is that if you wanted to do Lie theory with this bracket, with this Poisson bracket, because this the space of all functions is infinite dimensional, you run into these problems of infinite dimensionality. But if you remember this derivation, so this infinitesimal nature of the brackets, you can do something more refined, and instead of considering groups, you consider groupoids, which are finite dimensional. And the picture is a bit like this. The geometry of a Poisson manifold was described in this paper. It's can be very complicated. It actually is given by one of these singular foliations that I mentioned before. Each leaf is symplectic and so on. And so this looks like exactly like the infinitesimal version of the objects of the groupoid. And indeed, there is an algebra behind the Poisson structure. And you can think if this infinitesimal description comes from a groupoid. And what I wanted to highlight here is that when it does the simply connected integration, it's automatically symplectic. So the total space has a symplectic form, and the symplectic form is compatible with the groupoid structure in this way. So this is generalization of a cocycle condition for forms. So this gives rise to what is called symplectic groupoid, and vice versa. If you have a symplectic groupoid, so M in principle is just the objects of this groupoid, there is an induced Poisson structure on M. So this gives an interplay between Poisson manifolds M and symplectic groupoids. The source map actually preserves brackets. So this is called the symplectic realization, because this complicated bracket, as in that picture, that could vanish at a point or have different rank at different parts, is realized by something that is symplectic, it's non-degenerate everywhere. And vice versa, then it was proven that at least the germ of the groupoid structure is pretty much determined by the realization property. So, okay, this let me summarize. I'm going a bit fast, but let me summarize that there is this Lie theory for groupoids and algebroids that generalizes the story for Lie algebras and Lie groups. It contains lots of different geometric informations. And there is also this thing that sometimes the groupoids come with extra geometry in it. For example, a symplectic geometry. And this is very essential in the study of Poisson manifold. Even if you don't care about groupoids, you would quickly run into them because of this thing that the groupoid provides some sort of desingularization. So the symplectic picture is where there is only one leaf that is everything, right? So it desingularizes the geometry, and it has become a standard tool in the study of Poisson structures. Okay, this also is pretty much motivated by what I said about quantization, but I won't mention this much. So let me go quickly to the results that are related to my work with collaborators. So the first theorem that I want to mention is this one about, let's say, compatible differential forms. In the example that I showed before, we had a two form that is closed and non-degenerate and satisfied this equation. But actually, there is a Lie theory way more generally for all these forms. And they end up being characterized by infinitesimal data satisfying this set of PDEs. And this is a one-to-one correspondence. So this is the first theorem, the characterization of these compatible forms, the infinitesimal characterization of compatible forms. This can be put in action and obtain corollaries, but I don't have time to mention those. Here, I just mentioned many things. There are other geometric structures that live on the groupoid, which are compatible in a suitable sense, and that can be characterized infinitesimally. So and they have interest from many different ways, directions, and this is, I guess, a list of some results. So let me go quickly to the other two. Another thing is that, so if you think here, you say, if you already have a groupoid, then you get this one-to-one correspondence. But what about constructing this groupoid? And then we have results using an auxiliary differential equation that is called algebroid spray, generalizes geodesic spray, and so on. We can construct the groupoid structure through explicit ODEs, and this gives you a model near the units for any other groupoid. This generalizes widely, in a very big sense, the Baker-Campbell-Hausdorff series for Lie algebras. And also, the construction is very rich. If you multiply a Poisson structure by T and then do this construction and then expand it, you obtain something quite non-trivial, which is part of a famous formula that Kontsevich gave for quantization. So this is kind of a structural understanding of many things that were going around. And finally, I just mentioned this formula that in this particular model for integrating a Lie algebroid, the differential forms can be described by very explicit formula. Here, there is a flow of the differential equation, and then you transform it and you average. So this also was not known. We obtain it as a corollary. This works for any algebroid, actually. For all those geometries, this is true. And as I mentioned before, just to finish, even if you're not interested in the Lie theory part, you might be interested in the following, like this. if you have a Poisson structure that has this very singular type of geometry, can you find a bigger manifold, so a submersion, that is symplectic and that the brackets are faithfully encoded here, but now in a symplectic way? And this formula gives you the answer. The answer is always yes. So this is this idea of realizations, and you can change this Poisson structure with other structures that are also motivated by mechanics and other things. And you can apply these formulas to get realizations of all of them. So thank you very much.
Thank you, Alejandro. Is there any question for Alejandro? So I wanted to ask a question about the complex structures. So, so can you say anything about that?
Yes, actually, yeah, I would say that this, oops, yeah, here. So, for example, you can wonder if you have one of these groupoids, you can wonder about complex structures on them. I think of them as like this, as almost complex structures. And there is a natural way of saying when this complex structure is compatible with the groupoid. And indeed, there is an extension of this theorem that I mentioned above, characterizing this in infinitesimal terms. So this applies to Lie groups as well, but it's much more general. So there is an infinitesimal characterization, let's say JA, in terms of the algebra, the infinitesimal data. And there, if this is say simply connected condition, then this is one-to-one.
Okay.
So yes, this also works for complex.
Okay, thank you. Is there any other question for Alejandro? Well, if not, we can thank Alejandro again. Thank you.
Thank you.
Our next speaker is Anusha, and the next talk will be in 7 minutes.